In today's lesson, you'll determine whether a relationship is linear or nonlinear. The three formats that you'll be looking at today are graphs, equations, and tables. By the end of this lesson, you should be able to say that you can identify a linear function represented in different formats. In order to be successful, you have to understand that a graph that is a straight line is linear. But if it is curved or changes directions, it's nonlinear. If you have an equation, all of the variable powers must be 1. No variables in the denominator, no variables with other powers, no products of variables. And the last format is a table. Each table must have a constant rate of change. Let's get started. Here are some examples of linear equation graphs. Notice that every single graph is a straight line. All of these are linear. So let's take a look at some that are not. If your graph is non-linear, that means you are not a continuously straight line. You'll notice in graph number 1 that it starts to curve or change direction. This is non-linear. Graph number 2 is a continuously straight line. That's linear. Graph number 3 are two partial curves. Non-linear. Graph number 4 is a positively increasing from left to right linear graph. Continuously straight line. Number 5 and 6 both have either a change in direction or a curve. That makes them non-linear. Okay, let's move on to the second format. If you are looking at an actual equation or sentence of a relationship, you can tell that it's linear if both the x and y variables have powers of 1. That means their power is invisible. These are all examples of linear functions. As soon as I change the power, it's no longer linear. Another item is that linear equations cannot have products of variables. So that is not a linear function. And the reason for that is because a linear function can be written in slope-intercept form. You might recall that y equals mx plus b is slope-intercept form. If I were to manipulate that black equation with the product of x and y, in order to get y by itself, I would have an x in the denominator. And if you remember from your 8th grade studies, anything in the denominator has a negative power. And the rule is you have to have a power of positive 1, not negative 1. Remember, slope-intercept form is not the only arrangement that equation might look. All linear equations can be written in different ways, but the variable powers will always be invisible 1, whether it's written in slope-intercept form or whether it's written in standard form. Now for our final format. How can you tell if a table represents a linear function relationship? Well, it's simple. The constant rate of change is what's needed. So don't forget, the slope, or constant rate of change, is the ratio of the change in y over the change in x. If it is the same fractional value each time, it's a linear equation. So let's take a look here. The change in y is negative 15. The change in x is 2. Every time, change in y over the change in x is the same. That's a constant rate of change. It's kind of obvious when you look at the patterns. But the second table to the right is not as obvious, but it's still linear. And the reason for that is because the ratio of the change in y to the change in x, although the values are different, they're still the same. These fractions all reduce to 2. So although the pattern looks like it's changing, it's actually not. 4 over 2, 8 over 4, 6 over 3, 2 over 1, they're all the same. So that is a constant rate of change. Therefore, that table is linear. So let's take a look at when a table's nonlinear, like here. Notice the pattern of my y's, right? That's my numerator. The change in y is 1, then 2, then 6. But in my previous examples, just because the numbers weren't the same pattern didn't mean it wasn't linear. It was the ratio that mattered. So for this table, the ratio would be change in y is 1, change in x is 2. Change in y is 2, change in x is 2. You see those fractions? Not the same. That is not a constant rate of change. And the same is true for the second table over here. 2 over 1, 3 over 1, 4 over 1. Those are inconsistent patterns. Why don't you pause the video now and see if you can identify all of the linear functions on this screen. All right, let's see how you did. Now, more importantly, instead of just circling all that applied or identifying on your paper those that were linear, can you describe why they're not? Are you able to defend your reasons? So, if you circled this graph, that's not linear. You would circle this one because it is. So why didn't you circle that one? Can you tell me the reason? Yeah, because it's not a straight line. It's not a continuously straight line. How about the equations? Do you remember the rule? That's the only linear function there. The top one is not because it has a power of 2. And the bottom is not because that x has a power of -1. Now how about the tables? Did you find the patterns? Were they easy? That's linear. Were there any more? Plus 4, plus 4, plus 4. 4/3 is the constant rate of change. All right, that concludes our lesson on identifying linear and nonlinear functions.